Okay, so today I'd like to welcome Alexandra Fogg from the Dublin Institute for Advanced Studies. So thank you very much for joining us for this seminar. Alexandra is going to be talking to us about the effects of solar wind pressure pulses on the terrestrial magnetosphere. There'll be time for questions and discussion at the end. So if you want to put questions in the chat, I'll go through them at the end, or at the end, you can raise your hand and then we can discuss those. So Alexandra, I'm looking forward to hearing your talk, and please start whenever you're ready.
Okay, great. Thank you for that introduction. I assume you can still see my slides in full screen and my little laser pointer moving around.
Yeah.
Perfect. Okay. My name is Alexandra, and today I'm going to be talking to you about a few different ways we've been investigating the effects of solar wind pressure pulses on the terrestrial magnetosphere, with thanks to my co-authors below. And I'm just trying to change slide and it's not working. There we go. So I'm going to talk a little bit about sudden commencements to start off with, and that's the terrestrial effect of solar wind pressure pulses. Then I will present a sudden impulse case study. I am going to define all these terms shortly, so nobody panic. And then I'll talk about the statistical differences between sudden storm commencements and sudden impulses, and finally the effects of sudden commencements on Ireland. So firstly, a bit about me. I did my PhD at the University of Leicester on ionospheric convection, and since then I've worked at the Dublin Institute for Advanced Studies looking at terrestrial radio emissions, and more recently I'm now an Irish Research Council Fellow looking at sudden commencements. And here's a picture of our research group with some current and past members, and here's me with the giant purple arrow there. In case you can't see my Zoom window, you know who I am. Firstly, I'm going to introduce the Earth's magnetosphere in case anyone here is not familiar with that. I'm sure you all have some introduction to it, but just thinking of the perspective of solar wind pressure pulses, we have the Earth down here. The magnetopause is this sort of blue 3D surface here, and then the sun is somewhere off to the left, considerably further than the scale on this screen here, and in comes the solar wind along these streamlines. So the solar wind impacts the day side of the Earth's magnetosphere and compresses it. And if that solar wind flow dynamic pressure significantly rises, it will compress the magnetosphere much further. And then what we see is all these different label phenomena within get excited because of the compression, because energy is being communicated into the magnetosphere. So first, I'm going to talk a little bit about the driving event, and that's solar wind pressure pulses. So a pressure pulse is a rapid enhancement in solar wind dynamic pressure that's a blob of either faster and possibly also denser plasma. And authors have defined them in different ways over the years, but I will generally go with the definition from COCO 2011, where they say it's 3 nanopascals over 10 minutes or less. So I have an example of solar wind pressure time series here. So we have solar wind dynamic pressure on the y-axis as a function of time, and you can see a step change in solar wind dynamic pressure here. And in this paper, they actually detect these step changes by nonlinear least squares fitting of a step-like function, which are these red and blue functions here. So that's an example of a pressure pulse. And what are they driven by? Well, phenomena like CMEs and other similar phenomena where we have blobs of plasma coming out of the sun from an active region. But when the pressure pulse compresses the magnetosphere, and these effects are communicated throughout the magnetosphere, as I mentioned before, to all those different phenomena that we study, this is known as a sudden commencement. And what does that look like in a time series? Well, when we look at the H component of magnetometers, or equivalently, we look at SIM-H as a time series, we see a step change in SIM-H. So when we have a positive solar wind pressure pulse, so that increase in pressure, that's a positive sudden commencement. We also see rarely rarefactions in pressure, and that will be a negative sudden commencement. But I'm only going to talk about positive sudden commencements today, so we can forget about the rarefactions for the rest of this talk. So it has been shown that there's a correlation between the height of this pressure pulse and the height of this step change in SIM-H as well. So they are if one's bigger, the other's bigger sort of thing. They are related. So thinking a bit more about sudden commencements, I'm just going to define the terms. So just sort of a word to say, if you go to the literature, the terms aren't always used with this definition. So I'm going to define them how I'm going to use them today, and then you need to read the papers carefully when they use the terms, because they'll use different definitions. So a sudden commencement is when we've had that rapid change in solar wind dynamic pressure, which is communicated into the Earth's magnetosphere. So we see a change in DST or SIMH. If it's rapidly followed by a geomagnetic storm, and when I say rapidly, I mean within like 12 hours, that's a sudden storm commencement. If it's not rapidly followed by a geomagnetic storm, it's a sudden impulse. So those are the three different terms I'm going to be using. So sudden commencement is the umbrella term. Sudden storm commencement has an associated storm. Sudden impulse doesn't have an associated storm. And as I said, be careful in the literature there when you're reading the terms. So in 1994, Araki published a model of how sudden commencements propagate through the Earth's magnetosphere. So I have sort of redrawn their sketch here, and you can see here's the Earth. This dotted line is the original magnetopause position. In comes a solar wind pressure pulse and compresses the magnetosphere to a new position here. Compresses the magnetopause, to a new position here. As a result of that, the magnetopause current increases, and this compression is propagated tailward by compression of wavefront, which is indicated by this green dashed line here. And so for current continuity, this increased magnetopause current connects along the compressional wavefront with a current there. So within this current loop, we have increased current, and according to the right-hand rule, we have an enhancement in the magnetic field within the current loop as well. So when this compressional wavefront reaches the equatorial ionosphere, what we see is a step change in SIMH. So we see that increased magnetic field in the ground magnetometers. Thinking about the high latitude and polar latitude ionosphere, they feel the effects of the pressure pulse via Alfvén wave propagation. So when the compression hits these field lines here, the Alfvén waves propagate down them into the high latitude ionosphere, carrying with them field line currents and what we now know as region zero field line currents. What are observed in the ionosphere, and we have some related ionospheric lobe reconnection signatures, which are really tightly wound ionospheric convection signatures in the polar ionosphere on the day side. So that's the model predicting the effects based mostly on magnetometer observations. But since then, a few more observations have been done, and we've seen some other effects as well. So we see a restructuring of ionospheric electron density by the generation of ionospheric irregularities. So I have an example here of a superposed epoch analysis of some different sudden commencements. We have SIMH, solar wind dynamic pressure, and these are the superdome backscattered echoes in the noon sector, and you can see there's an increase. So superdome radars the return signal is backscattered off an ionospheric irregularity, which is an increase in electron density, a localized increase in electron density. And so essentially we're getting more echoes, which means there's more irregularities to bounce off. So we're seeing that restructuring of the ionosphere. Perhaps we're seeing particle precipitation as a result of the Alfvén wave propagation mode in the sudden commencement model. I've also got an example of some simulations here, which have shown region zero field line currents and some ionospheric convection vortices. So this is 2 minutes after the sudden commencement. You can see there's sort of blob here, but if we move towards 4.2 minutes, we've got an upwards blob here and a downwards blob here, or perhaps the other way around. No, I've got the other way around. I think upwards and downwards field line currents there. And that's again showing what Araki had predicted. It's also been shown that sudden commencements can drive geomagnetically induced currents, which we all know is really important because they can overload power lines and things like that. And we've also seen the superposition of Alfvén and compressional waves depending on the latitude and local time of the magnetometer station. So plenty of different observations to go along with that model there. So having described what's been done, I'm now going to say what I've done. So firstly, starting with a detailed case study of a sudden impulse. And this is some work I did as part of my thesis work. So firstly, I'm going to present observations of the pressure pulse and the sudden commencement in SIMH. So if we start at panel F down here, we have a clear step change in SIMH. This is a time series relative to this epoch time, which I'm marking as the beginning of the step change in SIMH. So we then went to look at the solar wind dynamic pressure in Omni, which is this panel here. So we have pressure in black, velocity in gold, and density in blue. And you can see there's a lot of gaps in the time series. But even with that, we can make some general comments. So we can say the pressure is lower here and it's higher here. And at some point between -8 and -2 minutes compared to this onset in SIMH, the pressure increase begins, but we don't know where. So we went to look at wind data. So wind was the only upstream spacecraft with data at this time. And that's presented in panel E here. So again, we have pressure in black, velocity in gold, and density in blue. And you can see there is a step change in the data and not really much else going on. But it appears as if the step change arrives, indicated by the dashed line here, after the onset in SIMH. And we interpret that as an issue with our propagation time. So we've only got one spacecraft available, so we've used a single spacecraft propagation time. And seeing as there's nothing else happening in this time series, I think it's okay to say this is related to this step change in SIMH, but we don't know the arrival time of the pressure pulse. We can only estimate from Omni that it's between -8 and -2 minutes before the SIMH onset. Looking at the auroral indices, we're not seeing any substorms happening. And looking at the IMF data, so again, this is from wind, so it's got this propagation time here. We can see we're in a northward IMF situation. BZ is in red here. And there's a slight BY rotation just here after the onset. So we know that with a little bit of BY, we change the reconnection sites on the day side of the magnetosphere, and then we get more energy potentially communicated into the magnetosphere. So that's important to bear in mind. But the dominant phenomenon in this interval is the compression of the magnetosphere, so the sudden commencement, which is driven by the pressure pulse. So the first thing to have a look at is the ULF wave observations. That by no means are these brand new observations. They have been seen before, but we are presenting them with our other observations because that enables the new observations to be compared with previously observed events. So I'm just going to focus on the magnetic north component here. So I have stations at the top are in high latitude stations, lower latitude stations at the bottom, and all these stations, these are magnetometers, supermag magnetometers, all these stations are about noon local time when the sudden commencement happens. What we see at higher latitudes is primarily alphane type signatures in the data. As we move to the more middling latitudes, we can see, again, we see the alphane wave, but we also see that the general magnitude of the signature is lower and then higher afterwards. So this is a superposition of both the alphane wave, which is that wave on a string type observation we're looking for, and the step change of the compressional mode. Then when we move down to those really low latitude stations, we're seeing primarily that step change in the data. And some indication that the compressional mode, particularly in this panel here, is arriving slightly later than the alphane mode. So those are there we're seeing the stratification of alphane and compressional mode propagation of the sudden commencement with latitude. Then we went to see, to have a look at the high latitude electrodynamics. So I'm afraid this is another slide which has 1 million panels on it, but I will do my best to explain them clearly. So on the left-hand side, oh, hello, someone speak then? No? Okay. So on the left-hand side, we have...
Yeah, sorry, no, we're still just getting some more quotes in, so we're not going to decide until...
On the left-hand side here, we have superdarn ionospheric convection maps. And in the center column, we have ampere field line current maps. And on the right column, we have them both together. So the superdarn ions, these are all magnetic latitude, magnetic local time maps, and they're all showing just the dayside ionosphere. So in the superdarn maps, the black lines are electrostatic equipotentials, or equivalently streamlines of ionospheric convection flow. Each dot is in a location where we have more than one superdarn backscattering observation, and the color of the dots and the length of the flagpole indicate the speed of the flow according to the scale here and this little scale at the bottom, and the flagpole points in the direction of the flow. In the ampere field line current maps, we have red as upwards current and blue as downwards current. So, and each row is 10 minutes apart, and we have the sudden commencement happening in this integration period in the middle here. So before the sudden commencement happens, the sudden impulse happens, we have a vaguely twin cell looking flow in the superdarn ionospheric convection maps. As we come to about 10 minutes before, we start to see the setting up of lobe reconnection, and that's not surprising because we're in a northward IMF situation here. As we get to sudden commencement onset, we can see the two lobe cells just here, and we can see that they're significantly enhanced after sudden commencement onset. This is maintained for a while. We've also got more vectors here. So again, we're getting more superdarn backscatter, so more ionospheric irregularities. This pattern is maintained for a while and eventually decays away. Looking at the ampere field line current maps, we have some indications of a region 1, region 2 field line current situation here beforehand. As we get to 10 minutes before, we start to see those region 0 field line currents. They are nice and clear at sudden commencement onset. That's our northward IMF signature. They are enhanced. We actually show this in a time series, which I haven't included here because it's for brevity. And they maintain for a while and eventually decay away. If we look at the two data sets together, and this is what makes this observation really novel and really exciting, is that we can see that the lobe reconnection cells are swirling quite neatly around the region 0 field line currents. And this is maintained and obviously, as I said, eventually decays away. So this is a novel observation of these two phenomena at the same time around sudden commencement onset, in this case, a sudden impulse. So we wanted to expand this study further, so we decided to look at some auroral images. I'm just going to take a sip of my drink. So we're using DMSP SUSY auroral images here. We have 3 passes. So this first pass is before the sudden impulse. This pass includes the sudden impulse time, and this is after the sudden impulse. So before the sudden impulse, we have a auroral oval we can see in the image. And then this pass starts at 2020, so that's 1 minute after the sudden impulse onset in SIMH. We're traveling across in this direction here, and we can see by about 2030, we're starting to see this cusp spot here. Now, we're very limited in how we can interpret the temporal resolution of this because this is the only pass we have at that time, but we are seeing some roughly co-located with the other ionospheric observations, cusp spot emission here. But we just don't know the onset time. We know that it's happening at the same time, but we don't know if it was happening already, whether it's strengthened or anything like that, because we only have one observation. But it's great to see it happening at the same time as those region 0 field line currents and lobe reconnection cells. So how does this fit into the propagation model? So I have a timeline of all those observations here. I realize I presented like several different things, but I'm going to try and bring them together here. So before the onset, we have northward IMF. So we see lobe reconnection and region 0 field line currents. Then sometime in this window here, we see the onset of the pressure pulse or the arrival of the pressure pulse at the dayside magnetosphere. Around SIMH onset, which is the beginning of the step change in SIMH, we see enhancements in what's going on in the dayside ionosphere. And then somewhere within this gray window here, we see the cusp emission in DMSP SUSY. And then eventually everything decays away. So what do we know about this? Well, we know it's an Iraqi 1994 type enhancement. The first observation with good vector coverage of lobe reconnection and region 0 currents together. And we've also seen that stratification of signatures of ULF waves with latitude. So it's a really nice case study and shows us that Iraqi model sudden commencement propagation quite well. So now I'm going to move on, having looked at a detailed case study and hopefully showed you the propagation of the sudden impulse through the magnetosphere. I'm going to look at some differences between sudden impulses and sudden storm commencements. So we've used the Observatory dell'Ebre event list. This is an event list that goes back to the 1800s, I think, but we just use the events from 1995 to 2017. And the reason for that is we want good omni data. Events are defined from equatorial magnetometer stations based on the gradient of the change in, essentially the change in time of the magnetic field. So what I've plotted here, the distribution of the parameters defining the sudden commencement. So we have the amplitude, that's the height of the step change, the duration, that's the width of the step change, and then the gradient, which is one divided by another. Just to have a look at the distribution of events, we can see the median of the amplitude is about 19 nanoteslas, and the median of the duration is about 4.6 minutes. We then went to have a look at solar cycle dependence, see if there's a difference between the two types of events. The great thing about using this event list is that we have events over a broad parameter space of 2 solar cycles, and we then further classify the sudden commencements into sudden storm commencements if SIMH reaches 40 nanoteslas within 12 hours of onset, and that's based on some previous work. If not, it's a sudden impulse. And throughout this study, we will have sudden storm commencements in purple and sudden impulses in pink. So what we've got here is a bar chart. So the purple bar and pink bar are stacked on top of each other. So the total height of the bar gives you the total number of sudden commencements. And you can see quite clearly that more events are observed during solar maximum and fewer during solar minimum. So there's a nice solar cycle dependence to the occurrence of these events. We then went to look at the magnitude of the events and whether the magnitude of the events varies with solar cycle. And this is a little bit less clear. So what I have in the top plot here is 1 dot for every sudden impulse, and it's the amplitude of the sudden impulse as a function of the onset time with the sunspot number overplotted. And you can see there are more events with high magnitude at solar maximum, but there's quite a bit of scatter. Now looking at the average sudden impulse magnitude per year, you can see that it's really not following the solar cycle as clearly, and there's a big peak just here. Looking at sudden storm commencements, they follow the solar cycle a little bit more clearly, and that makes sense because these are the events that are related to coronal mass ejections. And just to note that this scale goes much higher on panel B than it does on panel A. And you can see the average trace follows the solar cycle a little bit more clearly as well. So that's the solar cycle dependence. Not a great deal of difference between the two types of events. So then the question that we really wanted to answer was, why do some pressure pulses trigger geomagnetic storms and others don't? So essentially, why do some sudden commencements turn into sudden storm commencements? So the first thing we did was look at the driving event. And so we're looking at the amplitude of the sudden commencement, which is proportional to the amplitude of the pressure pulse. So what we find, so these are histograms of the amplitude, duration, and gradient again, but split into sudden impulses and sudden storm commencements. So sudden impulses in pink. We find that sudden storm commencements are driven by events with higher amplitude or gradient and shorter duration. So that's essentially saying that sudden storm commencements are driven by larger or faster compressions of the magnetosphere. So that's suggesting that the more energy we put in, the more likely we're going to have a geomagnetic storm as a result of the pressure pulse. The next step to determine why some pressure pulses trigger sudden storm commencements is to look at how the magnetosphere is primed. Essentially, what is it doing beforehand? So each of these plots is a histogram, again split into sudden impulses and sudden storm commencements. We have for BZ, BY, B total, flow velocity, flow density, flow pressure, the polar cap index, auroral electrojet index, and SIM-H. And these are, this is a histogram of those observations 30 minutes prior to the onset of the sudden commencement. So some of the key points that we're seeing is prior to sudden storm commencements, we're seeing southward IMF. For sudden impulses, it's northward IMF. So we're already in a situation where the magnetosphere is more easily being communicated energy from the solar wind prior to sudden storm commencements. We have higher B total and higher flow velocity and pressure prior to sudden storm commencement. So perhaps the magnetosphere is already a little bit compressed before the pressure pulse arrives. So we're more likely to kick off into a geomagnetic storm. And finally, we have greater activity in all three geomagnetic indices here. So we have higher polar cap index, higher auroral electrojet index, and more negative SIM-H. So essentially, the key conclusion is the magnetosphere is primed by higher activity preceding sudden storm commencements. So there's more going on, and then the pressure pulse comes, and we're more likely to end up in a geomagnetic storm. And then the final plot from this section of the talk is a superposed epoch analysis of those same parameters, again, split into sudden impulses and sudden storm commencements. So superposed epoch analysis is laying all the different events on top of each other and taking the average value of the parameter relative to the epoch time, where 0 is sudden commencement onset. And in these panels, I have BZ, BY, B total, flow, speed, density, pressure, polar cap index, auroral electrojet index, and SIM-H. Again, sudden impulses in pink, sudden storm commencements in purple, and the shade shows you the median absolute deviation, so the variability in the calculation of the median. So what do we find? We find that the BZ magnitude, as we've shown before, we are in southward IMF for sudden storm commencements beforehand, and northward IMF for sudden impulses, but this separates further after onset. You can see that we're going to, this magnitude increases further after onset. We see a greater increase in some of the parameters for sudden storm commencements than for sudden impulses, and that's for B total, for example, here. Flow pressure, so you can see there's obviously a greater flow pressure component there, the polar cap index and the auroral electrojet index. And for SIM-H, we're already starting off in a negative SIM-H situation. So it's not super negative, we're not already in storm time necessarily, but we're building up to that. So we're more easily, the magnetosphere is more easily being transformed into storm time as a result of the pressure pulse onset. So the conclusions from this part of the talk. So firstly, we've seen a solar cycle dependence to the occurrence and slightly to the strength of sudden impulses and sudden storm commencements. Sudden storm commencements followed the solar cycle slightly more. Sudden storm commencements are driven by larger or faster magnetospheric compressions. And the magnetosphere is primed by stronger solar wind coupling and stronger internal magnetospheric dynamics before we see sudden storm commencements. So essentially, sudden storm commencements are driven by larger driving events, and there's already things happening in the magnetosphere beforehand. So moving on to the final part of the talk, we're going to look at the effects of sudden commencements on Ireland. So I work at the Dublin Institute for Advanced Studies. We are a PI institution of the magnetometer network of Ireland. One of our PhD students made me this nice map here. You can see the different stations. So we have Armagh in the north, Dunsink, which is at the observatory where we work in the group. Burr and Valencia down in the south. So the network was founded in 2012, but Valencia has data going back considerably further. So we use the data that goes back to 1991. And that's because we want to do a large-scale statistical study, whereas some of these magnetometers are a bit newer. So we only have a few years of data. So the first thing we wanted to do is characterize the baseline conditions at Valencia. And essentially, we want to answer the question, how do we know what is a normal or abnormal value at Valencia? So essentially, so we can go back when we look at our sudden commencements and say, this is, this has significantly enhanced the Valencia data or it hasn't. And to do that, we extract some extreme values using extreme value analysis. And this is similar to work by Elvis 2020, where they predicted using a similar technique, return values in the AA index. So just to briefly describe the technique, we detect block maxima. So essentially we chop the data up into calendar years and extract the most extreme event from that year. We then fit a generalized extreme value distribution to these extremes, and then use that model to predict return values. So I'm just going to take a sip of my drink. So at first, we've done this for B, which is the horizontal component of the magnetic field. So that's a combination of N and E. And this is in supermag coordinates. So I have 3 plots here which assess the fit of the GEVD model. So the first one, we have the B observed at least once per return period as a function of return period. The observations are the triangles. The model is the orange line. And you can see fits better where we have more data. We don't have loads of data along here because we only have about 25 years of data. We have the PDFs here of the observations in the observed extremes in gray and the model in orange. And finally, we have a QQ plot, which I will explain in detail shortly, essentially comparing these two distributions here, where the circles are close to the line, they agree well. Where they're far away from the line, they don't agree so well. So you can see, again, it agrees better at the lower values where we have more data. We have less observations up towards these high nanotesla values. Essentially, the key result from this is that we determine the return values. So we can say that every 25 years, Valencia will see an observation of B that is above 762 at least once. So if we're then seeing as a result of a sudden commencement, for example, an observation of 500 nanoteslas, we can say, well, that's a 10-year event. So that's giving us a baseline to compare to compare our sudden commencement results with. I've also done this for dBdt, and the fitting of the GEVD model is slightly better. You can see that from each of these plots, particularly the QQ plot. If you're looking here, circles are much closer to the line, and we only have that one data point that's straying away from the line. Again, here we have the return values. So every 15 years, for example, dBdt is going above 2.73 at least once. So that's giving us our baseline of what is an extreme value. But before we look at sudden commencements, we wanted to assess the distribution of the extremes that we detected with magnetic local time. And this is because when we were looking at, so if you're interested, the MAGI network has storm alerts. And I noticed that these always seem to come, and this is for a high K index. So essentially when we're seeing a high activity, and these emails always seem to come when Ireland was at a particular local time. So we can look at this statistically now. And this is a local time histogram. So we have noon at the top, dawn on the left, midnight at the bottom, and dusk on the left. I think I've got left and right the wrong way around there, but hopefully you are following my mouse. So each one of these points shows the number of extremes that were observed in that local time bin. These are 1 hour local time bins. We have crosses for B and circles for dBdt. And you can see the number of extremes observed in the pre-midnight sector is much higher than everywhere else in local time. And we're linking that back to substorm activity because we know that substorm onset is often observed in that pre-midnight sector. And that's where we see those big excitations in the aurora as well. So now moving on to look at the sudden commencements, I'm going to describe a bit about quantile plots first. So I have a figure here from Tyndale and Chapman. And you can see we have two cumulative distribution functions, red and blue. And the cumulative distribution function is telling you the probability of observing a value above a certain place on the x-axis as a function of the x-axis. So what we do is select quantiles from this plot. So essentially along the y-axis here, we have values going up to 100%. And we select a place Q1 here, which may be 25%, for example, and then trace along and find the x-axis value of red and also of blue. And then we plot these x-axis values against each other here. And you can do this for as many quantiles as you like. And we plot them with a y equals x line. And if it's on the y equals x line, they agree. If it's not, then one of the distributions is, well, the distributions are different. So the first thing we wanted to look at was the short-term consequences of sudden commencements, and we look at that using the horizontal component of the magnetic field again. So we have these quantile plots. I have separated the events into events where iron was at dusk, noon, and dawn. And then we have 3 windows after sudden commencement onset, 0 to 15 minutes, 15 to 30 minutes, and 30 to 45 minutes. One of the key observations you see straight away is that as we increase to increasing B, I should have said these values are on the y-axis, these distributions are on the y-axis, and the x-axis is all the observations at that magnetometer station at this local time. The first thing you immediately see is as we increase in B, the sudden commencement distributions get more different to the all-time distribution, and that's true for all 3 of these plots. And is actually true for most of the quantile plots I'm going to show. But something that's immediately, well, not immediately, something that we also see from these plots, if you look at the triangles being immediately after sudden commencement onset, the squares being longer after sudden commencement onset, you can see here at dawn, the triangles are least different from the normal, and the squares are most different from the normal. And we interpret that as, so we're at dawn at onset, and in that 30 minutes it's taken after onset, we have rotated towards the compression region. We've rotated towards noon, only by half an hour of local time, but we're seeing more differences there. And the opposite is true for dusk. The most different period is the period immediately after onset, and that's when we are closest to the compression region. So these are the same plots, but this is for dB/dt instead of B. And we have generally, so again, we are increasing the differences with increasing dB/dt, and that's true for all of them. But generally, the 0 to 15 minute window is most different from the normal. And that makes sense because that 0 to 15 minute window includes the step change itself. And that's where we have the highest dB/dt related to sudden commencement onset. And then finally, we have a look at the long-term consequences of sudden commencements. So here I haven't split the events up based on where Ireland was in local time at sudden commencement onset, but just purely looking at all the events for B and dB/dt and for 3 different time windows. So we have 0 to 12 hours, 12 to 24 hours, and 24 to 36 hours. And what we can see, again, the differences increase with increasing B and, increasing dB/dt and increasing B. And that the 12-hour window, particularly for dB/dt, is most different to normal. But even the 24 to 36-hour window, even though it's moving back towards the line compared to the other windows, it's still significantly different. So we're still seeing 24 to 36 hours after the sudden commencement that we're not in a normal situation. We are in a driven situation. So this is my final conclusion slide. You may be relieved to know we have determined what are the effects of sudden commencements on islands. So firstly, we determined return values of extreme B and dB dt values, which we will use in some future work to compare with the values following sudden commencements. We see more of these extremes at pre-midnight local times. And finally, we're observing that increased B and increased dB dt following sudden commencement onset. And just before I finish, just one more thing. I'd like to advertise that along with Harneet Sanger and James Waters, we are hosting an RIS specialist discussion meeting on the 10th of March. It will be one of the buildings in the Burlington courtyard, but that's not confirmed yet. But it'll also be online. The abstract deadline is the 27th of February, and the title is Solar Control of Energy Transport and Deposition in the Terrestrial Magnetosphere-ionosphere System. And I'd love to see as many of you there as possible. It's free for RIS members, I think. So hopefully some of you will see that and be super excited and want to come along. It would be great to see you there. But I'll just leave my conclusion slide up. But that's it from me.